In this lecture, we are going to discuss weak acid and weak base calculations, particularly how to calculate the pH of the solution. For this material, the first topic we will discuss is the percent ionization of a solution. Next, we will consider the rigorous calculation of pH for weak acids and weak bases. And finally, we will address a shortcut method for calculating the pH. First, we need to discuss the percent ionization of a solution. Since a weak acid or base does not completely dissociate in water, we need a practical measure of the extent of dissociation. We learned in the previous lecture that the value of Ka or Kb will tell us this, but they are not the most practical way of thinking about the extent of dissociation. The percent ionization is defined to be the amount of conjugate base at equilibrium divided by the formal concentration of the acid, all times 100%. For a weak acid HA, the reaction generates both A- and H3O+. Recall that the concentration of A- is equal to the concentration of H3O+ at equilibrium. This results in two ways to write the percent ionization for a weak acid. The percent ionization can be defined as the concentration of the conjugate base at equilibrium, A-, over the formal concentration of the acid, HA, times 100%. But this is also equal to the concentration of hydronium ion at equilibrium divided by the formal concentration of the acid, times 100%. If we're dealing with the weak base B, which forms Hb+ and OH- in water, we can also write for this solution the percent ionization is equal to the concentration of the conjugate acid, Hb+, divided by the formal concentration of B times 100%, or the concentration of hydroxide ion at equilibrium, divided by the formal concentration of the base times 100%. Now let's look at several examples. First, we have a 0.075 molar solution of formic acid, and this solution is found to have an equilibrium concentration of formate ion, HCOO-, equal to 3.7 times 10 to the negative third molar. Calculate the percent ionization of this solution. Since we are told the concentration of the conjugate base of formic acid, we can directly calculate the percent ionization. In this case, the percent ionization is equal to the equilibrium concentration of HCOO- divided by the formal concentration of the formic acid, times 100%. This gives 3.7 times 10 to the negative third molar divided by 0.075 molar times 100%, or 4.9% ionization. In our second example, we have a 0.125 molar solution of nitrous acid, which has a pH of 2.16. Calculate the percent ionization of this solution. Notice in this case we're given the pH of the solution, and so we first have to calculate the hydronium ion concentration from this. Recall that this is equal to the nitrite ion concentration, which is our conjugate base. We find that the hydronium ion concentration is 10 raised to the negative 2.16 power, or 6.9 times 10 to the negative third molar. We can now find the percent ionization, which is the hydronium ion concentration at equilibrium divided by the formal concentration of the nitrous acid times 100%. This is 6.9 times 10 to the negative third molar divided by 0.125 molar times 100%, or 5.5%. Now let's consider a basic solution. We have a 0.084 molar solution of cyanide ion, which has a pH of 11.04. Calculate the percent ionization of this solution. Recall that we need the hydroxide ion concentration at equilibrium to solve for percent ionization. And so the first step is to find the pOH of the solution. This is equal to 14.00 minus 11.04, or 2.96. We can now solve for the hydroxide ion concentration, which in this case is equal to the conjugate acid concentration. The hydroxide ion concentration is equal to 10 raised to the negative 2.96 power, or 1.1 times 10 to the negative third molar. Lastly, we can calculate the percent ionization. This is equal to the equilibrium concentration of hydroxide ion divided by the formal concentration of the cyanide ion times 100%, or 1.1 times 10 to the negative third molar, divided by 0.084 molar times 100%, or 1.3%. There are a few more points we need to make about percent ionization before we move on. The first, hopefully, is obvious. The larger the value of K, either Ka or Kb, the larger the percent ionization. The second is not quite as obvious. The more dilute a solution of weak acid or weak base, the larger the percent ionization. This is actually due to Le Chatelier's principle. If we write the reaction quotient for our weak acid expression, we get Q is equal to the concentration of H3O plus times the concentration of A minus divided by the concentration of HA. As we dilute the solution, all of these concentrations become smaller, but because we have two terms in the numerator, it gets smaller at a faster rate than the denominator does. This causes Q to become smaller as we dilute. And recall from a previous lecture that as Q gets smaller, the equilibrium will shift toward products. This causes a greater extent of ionization as we have a more dilute solution. This now puts us in a position to solve for the pH of a weak acid or weak base solution. Recall that this is the second type of equilibrium problem that we've encountered, where we know the value of K and we need to calculate the equilibrium concentrations. Unfortunately, as you recall this type of problem, you should immediately think about solving quadratics. This was the most difficult type of problem we have encountered so far in this class. There is some good news, though, that even though weak acid, weak base problems may still involve solving a quadratic, they are much easier to set up than previous problems because they always will take the same quadratic form. The beginning point for our derivation of the quadratic form is to recall our discussion of solving for Ka in the previous lecture. We have the weak acid HA with some formal concentration F sub HA. The ice table we built has the following form. Please pause this video for a moment and recall this table. The Ka expression that we built takes the following form. Since Ka is equal to the concentration of hydronium ion times the A minus concentration divided by HA, this is equal to x squared divided by the formal concentration of HA minus x. In this case, we need to solve for the variable x. The first step is to multiply through by the denominator, and this gives x squared is equal to Ka times the quantity formal concentration of HA minus x. When we distribute on the right-hand side, we get x squared is equal to the formal concentration of HA times Ka minus Ka times x. And this gives us our quadratic form, which looks like x squared plus Ka times x minus the formal concentration of HA times Ka is equal to 0, where in this case x is equal to the concentration of hydronium ion at equilibrium. More importantly, we can do the exact same derivation for the weak base, which has an equilibrium constant of Kb and a formal concentration of F sub b. The resulting quadratic looks almost identical to the previous one. In this case, x squared is equal to Kb times x minus the formal concentration of the base times Kb equal to 0, where now x is equal to the hydroxide ion concentration. Let's consider an example of chlorous acid, which has a pKa value of 1.96. You're given a 0.072 molar solution of chlorous acid in water. Calculate the equilibrium concentrations of chlorous acid, the chloride ion, and hydronium ion, as well as the pH of the solution. The first step is to find the value of Ka from pKa. Recall that this is equal to 10 to the negative pKa power, or 10 to the negative 1.96 power. Ka is equal to 1.1 times 10 to the negative 2. The next step is to find the value of the formal concentration of the chlorous acid times Ka. This is the last term in our quadratic. We find this by multiplying 0.072 times 1.1 times 10 to the negative 2, which is equal to 7.9 times 10 to the negative 4. Now we can solve the polynomial. Recall that it takes the form x squared plus Ka times x minus the formal concentration of the acid times Ka is equal to 0, or x squared plus 1.1 times 10 to the negative 2 times x minus 7.9 times 10 to the negative 4 is equal to 0. When we substitute into the quadratic formula, we get negative 1.1 times 10 to the negative 2 plus or minus the square root of 1.1 times 10 to the negative 2 quantity squared minus 4 times 1 times negative 7.9 times 10 to the negative 4, all divided by 2 times 1. This simplifies to negative 1.1 times 10 to the negative 2 plus or minus the square root of 3.3 times 10 to the negative third, all divided by 2, or negative 1.1 times 10 to the negative 2 plus or minus 0.057 divided by 2. This becomes negative 5.5 times 10 to the negative third plus or minus 0.029. This gives two possible roots. The negative root is not realistic, and so we have a concentration of hydronium ion of 0.024 molar. We now have sufficient information to calculate the equilibrium concentrations. First, recall that the hydronium ion concentration is equal to X, or 0.024 molar. Likewise, the chloride ion concentration is equal to X, which is 0.024 molar. The chlorous acid concentration is equal to the initial formal concentration of the acid minus X, or 0.072 molar minus 0.024 molar, or 0.048 molar. And lastly, we can find the pH of the solution, which as always is the negative log of the hydronium ion concentration, or equal to negative log of 0.024, and this gives a pH of 1.62. Our next example is for a base. The value of Kb for methylamine is 4.4 times 10 to the negative 4. You have a 0.105 molar solution of the methylamine in water. Calculate the equilibrium concentrations of methylamine, the methylammonium ion, and hydroxide ion, as well as the pH of the solution. In this case, we can directly calculate the value for the formal concentration of the methylamine times Kb. This is equal to 0.105 times 4.4 times 10 to the negative 4, which is equal to 4.6 times 10 to the negative 5. Our polynomial takes the form x squared plus Kb times x minus the formal concentration of the base times Kb is equal to 0, or x squared plus 4.4 times 10 to the negative 4 times x minus 4.6 times 10 to the negative 5 is equal to 0. I will not read out the values when solving for the quadratic formula. Please pause this video and work through this quadratic to ensure that you get the correct answer. Now we can solve for the equilibrium concentrations. First, the concentration of the hydroxide ion is just equal to X, or 6.6 times 10 to the negative third molar. Likewise, the methylammonium ion concentration is also equal to X, or 6.6 times 10 to the negative third molar. The methylamine concentration is equal to the formal concentration of the base minus X, or 0.105 molar, minus 6.6 times 10 to the negative third molar, which gives 0.098 molar. Then we can find the pOH of the solution, which is negative log of the hydroxide ion concentration, or negative log of 6.6 times 10 to the negative third, which is equal to 2.18. And finally, the pH, which is 14 minus the pOH, or 14 minus 2.18, which is equal to 11.82. It turns out that there is a very nice aspect of weak acid, weak base problems, and that is that there is a well-defined shortcut method for solving the equilibrium under certain conditions. So let's go back to the starting point, the Ka expression. Recall that Ka is equal to x squared divided by the formal concentration of the acid minus x. If Ka is sufficiently small and the formal concentration of the acid is sufficiently large, the value of x will be much smaller than the value of the formal concentration. This means that we can simplify the expression. Ka is equal to x squared divided by the formal concentration of Ha minus x, which is now approximately equal to x squared divided by just the formal concentration of the acid. This results in the fact that x squared is approximately equal to the formal concentration of the acid times Ka, or that x, which is equal to the hydronium ion concentration, is approximately equal to the square root of the formal concentration times Ka. There is a corresponding expression for bases. Assuming that Kb is sufficiently small and F sub b is sufficiently large, then x, which is now equal to the hydroxide ion concentration, is approximately equal to the square root of the formal concentration of the base times Kb. So this leaves us with the important question, what does it mean that K is sufficiently small and F is sufficiently large? Well, it turns out that this is the same as saying that the percent ionization of the species is less than 5%. There's actually a very simple rule. If you calculate the ratio of the formal concentration of the acid over Ka, or the ratio of the formal concentration of the base over Kb, these must be greater than 375. However, regardless of how big that ratio might be, you still must calculate the percent ionization to verify that it is smaller than 5%. Let's look at an example. Let's calculate the pH of a 0.013 molar solution of acetic acid, which has a Ka value of 1.8 times 10 to the negative 5. The first step is to test for the shortcut. We need to calculate the ratio of the formal concentration of the acetic acid over Ka, which in this case is equal to 0.013 divided by 1.8 times 10 to the negative 5. This gives us a value of 722, which is indeed greater than 375. Our shortcut method should work. We can now calculate the hydronium ion concentration as the square root of the formal concentration of acetic acid times Ka, or the square root of 0.013 times 1.8 times 10 to the negative 5. This gives a value of the square root of 2.3 times 10 to the negative 7, or 4.8 times 10 to the negative 4 molar. Recall that before we go any further, we must check the percent ionization. In this case, the percent ionization is the concentration of the hydronium ion divided by the formal concentration, or 4.8 times 10 to the negative 4 molar divided by 0.013 molar times 100%, which gives a value of 3.7% ionization, which is under 5%. So our results should be good. We can now calculate the pH of the solution, which is the negative log of our hydronium ion concentration, or the negative log of 4.8 times 10 to the negative 4, which is equal to 3.32. We are done with the problem. Note that if you solve the actual quadratic, and for practice you really should, you should get a concentration of hydronium ion equal to 4.7 times 10 to the negative 4 molar and a pH of 3.33. Notice that our approximation is sufficiently close to our actual values to warrant its use. This concludes the lecture on calculating pH for weak acid, weak base solutions. We learned several important ideas. First, the percent ionization is a measure of the extent of ionization in a weak acid, weak base solution. Secondly, the percent ionization increases either as Ka or Kb increases, or as the formal concentration of the species decreases. Third, when solving for the pH of a weak acid or a weak base solution, we can use the exact same quadratic form every time. Fourth, if the ratios of the formal concentration of the acid over Ka or the formal concentration of the base over Kb are greater than 375, then the shortcut method can be used. But lastly, no matter what the value of the ratio, you must verify that the percent ionization is less than 5%. If it's not less than 5%, you must use the quadratic.